A conductor suspended by two flexible wires as shown has a mass per unit length of 0.04 kilograms per meter. What current must exist in the conductor for the tension in the supporting wires to be zero when the magnetic field is 3.6 Tesla into the page? And what is the required direction for the current? The problem gives us the mass per unit length for the conductor of 0.04 kilograms per meter and the magnetic field which is oriented into the page and has a magnitude of 3.6 Tesla. This magnetic field will apply a magnetic force to the conductor because there is a current flowing through the conductor. We need to find the magnitude and direction of this current such that the tension in the supporting wires is zero. So let's draw the forces that are acting on the conductor. We have a tension force oriented up in the left wire and the tension force oriented also up in the right wire. And we have the force of gravity acting on the conductor. Now, if the tension forces are supposed to become zero, then if they disappear, clearly, in order for this conductor to be in equilibrium, there must be a force that's oriented upward that balances the force of gravity. This force must be the magnetic force, the force applied by the magnetic field. Since the conductor is in equilibrium, we can write that the sum of all forces acting on this conductor is zero. The forces acting on the conductor are the two tension forces, the force applied by the magnetic field, and the force of gravity. The two tension forces are going to zero because the problem says that the tension must be zero for a specific value of the current. And because the magnetic force and the force of gravity are oriented in opposite direction, it means that they must cancel each other out. And if we consider the positive direction to be oriented up, we can write that the force applied by the magnetic field B minus force of gravity equals zero. The magnitude of the magnetic force applied by the magnetic field is calculated as the current times the length of the conductor times the magnetic field. If we take this equation and replace it in the equation for the sum of all forces equals zero, we get that the magnetic force written as current times length of the conductor times magnetic field equals the force of gravity as mass times gravitational acceleration g. From this equation, we find that the current can be calculated as mass times gravitational acceleration g divided by the length of the conductor and the magnetic field. We know everything. We don't know mass and the length, but we know mass divided by length. And we replace that with 0.04. Gravitational acceleration, instead of 9.8, I took it 10 just for ease of calculation. And the magnetic field is 3.6. And we obtain a value of 0.11 amps for the current that is flowing in this conductor. Now, we need to figure out the direction of this current. We know that the magnetic force is oriented upwards, which means when you use the right hand rule, the thumb of your right hand has to be oriented upward. The four fingers of your right hand have to be oriented along the conductor, either to the right or to the left, in such a way that you can curl the four fingers into the screen, because that is the direction of the magnetic field. So clearly, the only way you can do that is if the four fingers point towards the right. So the direction of the current is from left to right through the conductor.